Welcome, everybody. Welcome to Relatorium. I'm Karen Little. I run the YouTube channel called Awesome Reversible Knitting. I had the privilege to give a Relatorium talk a few years ago, and I'm thrilled to moderate one now. Thank you so much, Stefan, for asking me to. Welcome to Parker Adey and Ness Schattman, who will give a talk on the art of braiding algorithms. I'll be watching the chat if you have questions, and of course, we'll have time at the end of the sessions as well. I'm ready with my string. I've got my string. Does everybody have their string? Parker and Ness said that it works with or without, but I think it's much more fun with about a piece about this long, and then just okay, over to you, Parker and Ness.
Awesome. Well, thank you. Again, it's an honor to be here. Irfan is a regular attender of the University of Toronto Scarborough Campus Computer Mathematical Sciences undergraduate seminar, UTSC undergrad seminar, and it's nice to be invited to your seminar, Irfan. So this is some work that Ness and I have been doing over the last, since January?
Yeah.
The last year. We're going to take you very much through the history of string figures very, very quickly. What we're telling you is advanced string figure mathematics. Okay, this is the kind of thing that takes many months of goofing around to get to. This is also in preparation for an upcoming workshop that we're giving at Bridges. So this is the online version of the workshop. So Bridges is a mathematics and art conference. It's happening this summer at the University of Galway, Ireland. If you happen to be near Ireland, you should come. It would be great. They chose their logo based on our talk. That's a lie. That's not true at all. But it looks like one of the relations that we're going to show you in our talk later. So cool. So thank you for coming. The outline is quite ambitious. We're going to tell you about string figures, how mathematicians viewed them, how anthropologists viewed them. We're going to show you a particular relation that sparked this whole investigation. And then we're going to go into braid theory and loop braid theory. There's really two stories in this talk kind of running in parallel. So the one is the story of search for good notation. How do we denote string figures and string figure procedures? And then there's another thread about kind of how we found ourselves deep in algebraic topology and how unexpected that was. Cool. Please interrupt us. You're totally welcome to interrupt us. Please ask lots of questions. We're here to kind of demo this material and chat with people about it. So we'd love if we had a good conversation. Okay. All right. So what are string figures? These are culturally universal games played with a simple loop of string. So this figure, Brokos, was recorded in 1st century Greece in a treatise on medical knots, but it's made all over the world. People in South Africa make it and call it the sun. It is played, people play with string everywhere. There are more cultures that play with string than play catch with a ball. The people who don't play with string also haven't like domesticated dogs. So very, very, very universal. All cultures at some time and some place have played with string. Just as a show of hands, people in the audience, did you play with string as a kid? Seen these games? Yeah. This is a thing, right? So string figures represent all kinds of different stuff. Ness, can you show us Kura?
Oh, sure. Actually, should I?
Yeah.
Okay.
Wait, sure.
So Cora is quite similar to the Brokos figure that you saw earlier. It's just got sort of two of these.
So what Ness just did is like 300 words to describe in English. Like that's like, there's a lot of moves that just happen there. In this workshop, we're not going to teach this. If we were in person, we'd carefully walk everyone through playing with these figures. This is the online version, so there's going to be fewer figures that we're teaching. But there's a figure from Australia. Okay, here's steal a weight string back.
Yep.
Here's a fish spear. Okay, so this is a nice string figure, a nice introductory string figure. I taught it to my 5-year-old kid. This is something that...
Sorry, I'm just getting another white string.
Oh, sure, of course. Yeah. Yeah, so these are approachable. So this is one of the first published string figures, fish spear. And why did anthropologists get into string figures? So we're going to start looking at the history of anthropologists and this stuff. So it all begins with Tyler's 1880 paper, Remarks on the Geographic Distribution of Games. So he says, next, as to a game which we consider still more childish, Mr. Wallace, being one wet day in a Dayak house in Borneo, to amuse the lads, took a piece of string and showed them Cat's Cradle. When, to his surprise, he found that they knew more about it than he did, a native boy taking it off his hands and making several new figures, which quite puzzled him. So Tyler is writing at the end of the 19th century, and he's an anthropologist interested in how did culture spread throughout the world. And he proposes that games are these kind of like discrete algorithms that have to be transmitted kind of mouth to ear. Like you have to learn a game from someone else. There's no way you can just stumble into knowing a particular game. So at that time, the end of the 19th century, people were interested in this diffusion theory of culture, that these cultural artifacts have to move person to person. And if you just trace where things diffused, you could say, find out where culture began or where a particular cultural artifact was found. Okay. So Tyler publishes this paper. People start noticing, okay, string figures, various kinds of games are culturally universal, but people can't record them. There's no way to write them down. So they like sketch the final positions, but there's no way to actually say what the string game was until Rivers and Haddon in 1902 published a paper, A Method of Recording String Figures and Tricks. We are informed these figures are much more complicated than ours, and that they represent various natural and artificial objects, sometimes in a state of rest, sometimes in a state of motion. So they publish a short description of how to write down string figures. And they publish this first figure, this fish spear. So this is the first figure recorded in Rivers and Haddon using their nomenclature for how to describe string figures. Mur Island is very small. It's 5 kilometers squared. Very tiny, 4.89 kilometers squared, actually. And it's in the Torres Strait, which is between Australia and Papua New Guinea. So very, very, very specific spot. So how do mathematicians get into it? Well, Rivers and Haddon are anthropologists at Cambridge, and Rouse Ball is a mathematician at Cambridge. And I sort of imagine them like bumping into each other in the quad. Oh, say, old chap, what are you doing there? Oh, making string figures. And then they, you know, then mathematicians get into the picture of string figures. So in 1920, Ball gives a talk at the Royal Society, very prestigious venue, where he shows people some string figures and says, "It is a truism, and in fact a truth as well, that all sensible people have hobbies. I am not alone in finding that the collection of string figures is an agreeable hobby, and that it may be added a very cheap one. Moreover, the figures are easy to weave, they have a history, and are capable of many varieties." Pretty interesting. But this is where the sort of the process of mathematization begins, I think. So we start noticing commonalities among these string figures. And now we're going to teach you a string. So if you could get your string out, we'll actually show you a thing. So a remarkable feature is that a large number of the figures begin in one way. In this, the tips of the thumbs and little fingers of each hand are put together and then put from below into the loop of string. So you get, doesn't really fit on camera very well, but like this, into the loop. And then you have this big shape. I'll go back a bit. There you go. Now you have a big rectangle.
Yeah.
So now it is a math talk. Cool. I can't see all the videos simultaneously. I'll just assume that people are pretty good. You have, okay, yeah. Jack Love totally has it. Great. Okay, cool. So now you start having named positions. This is called first position. This is where many things begin. Lastly, the palmar loop on each hand is picked up by the back of the index finger, and this is named opening A. So we start first position, index finger picks up palmar string. Cool. You have now made the beginning of 90% of string figures. Okay, so there's this kind of common opening position. And we're starting to name things. We have this artifact, and we're starting to name particular parts. Are things people curious about, want to ask there? So we've got it.
I do have a question.
Yeah, of course.
Yeah, what do you mean by exactly like the string you just made makes almost all of the string figures possible?
Yeah, so in the literature, right? Maybe there's, I don't know, maybe 5,000 string figures written down, and maybe 4,000 of them begin with opening A. So it's like a very common opening. So in almost all string figures, you start with this position. Yeah, that's a nice one. So in the diffusion theory of cultural transmission, we suspect that someone figured this out very early on, and then they told people, and then that spread all over the world. Maybe that's what happened. We don't know. Cool. All right. So there's opening A. Ta-da! Opening A is lovely. Okay. So Ball is writing in 1920, and then Amir Moez is a faculty at Texas Tech, and he's writing in 1965, and he writes a little pamphlet called Mathematics and String Figures. How do these things relate? And in it, he introduces a notation, a particular nomenclature for doing these things. So opening A becomes OA, right interchange becomes RI, left interchange becomes LI, and so on and so forth. And he gets these formulas that describe how to make string figures. So he says, opening A, thumbs on the right-hand side, go over S1 plus S2 plus S3, et cetera, et cetera, et cetera. And this notation is sort of a shorthand for these long English descriptions. You have a formula which is sort of compressing a lot of text. And Moez recognizes the inadequacy of this notation. He says, as we see here, our notations are only adequate for figures with lozenges. We shall not deprive the reader from the enjoyment of discovery of more adequate notation. I think we should like pop that into every book in math ever. Put that into every calculus book, and maybe more people will do non-standard analysis or something.
Sorry, what is lozenges?
So the section of the book that where this occurs shows this figure, and these lozenges are the little diamond shapes. This figure, much like Brokos that I showed you earlier, is also somewhat culturally universal. Lots and lots of people make this. Lovely figure. But yeah, so this is still this is a notation, but it's kind of like knitting notation, like K2, P2, or it's a compression of English text, essentially. You can't do math on this yet. Cool. So the story continues. In 1978, Hiroshi Noguchi, a Japanese mathematician, so Noguchi was working in like homotopy theory, algebraic topology, has some papers in the Annals, so pretty serious topologist. And then Philip Noble, an Anglican missionary stationed in Papua New Guinea, they found International String Figure Association to preserve and document these things. So they put out a bulletin, and you can see them making this figure with the lozenges, the figure I just made. That's actually the logo of ISFA. Excellent. Okay, so we're primarily going to use this as our point of departure for the math. So in 1988, Thomas Storer, one of the first indigenous people to receive a PhD in mathematics, publishes this big monograph, thick monograph, on string figures. And he says in the introduction, the wordy ramblings of collectors were too imprecise to satisfy, and topological knot theorists apparently dismiss the entirety of the string figures of the world as trivial. And although I learned a great deal from both groups of writers, I hungered for an approach that was neither too weak to be effective, nor so strong that it identified as trivial, at that, all the objects of my insatiable interest. So he's a mathematician, writing end of 20th century, has thought a great deal about these things, and he introduces this notation that is shown at the bottom of the slide for Osage diamonds. So this is the same figure as Amir Mo is notated, but looks, I don't know, much more, yes, looks much more kind of notation heavy. There's arrows, underlining. There's this little end of proof symbol. And he's introduced a kind of a domain-specific language for talking about string figures. And it turns out that this is approaching something that you can do mathematics with, you can prove theorems about. So this gets adopted by the International String Figure Association, as some parts of it get adopted as kind of standard nomenclature. So Ness, do you want to take over from here?
Yeah, so this diagram is that same opening A that you're seeing earlier. So a little note of caution, I'm displaying this the opposite way, so you're seeing my thumbs on top. But the idea of this nomenclature is to divide these strings into loops and name them based on where they occur on your hands. So the first thing that you do is you start by naming your fingers. So 1, 2, 3, 4, 5. And then the loops get named based on the fingers they're on. So
Do you want me to be Van White?
yes. So this is my 1 loop here. And then my 2 loop is these 2 strings on my index fingers, and then my 5 loop is these 2 on my little fingers. And then you can also name the individual strings based on whether they are sort of facing towards me, like the near strings, or like away from me, so the far strings. So my 5 far string, for example, is the one that's furthest from me on my little finger, whereas my 5 near string is the one that's on that sort of that near side of my little finger towards me when I'm holding the figure like this. And we can go on, we can describe our 1 near and our 1 far, and so on and so forth. And so just looking back at like Storer's notation, which can look, a little bit arcane at first glance, we can already see these sort of references to how our fingers move and the sort of strings they pick up. So the first step just says drop both strings on your 1 finger. And then the next step says go under everything and pick up this 5 far string from below, and so on and so forth. So the question that Parker mentioned earlier was like, how much can we actually do math on this way of notating it, and how much is this just like a more condensed way of saying what string figure collectors had already been saying in English? And it turned out that we could start to do a little bit of math on this once we did just one further abstraction. So this book, String Figures as Mathematics, was simultaneously a mathematical and an anthropological treatment of string figures. And for our purposes today, what that introduced was a new mathematical construct for thinking about string figures, namely the loop-based interpretation. In Storer calculus, what we're primarily focused on is individual strings. Am I picking up this string? Am I pulling it? Whatever. Am I releasing it? Am I twisting it? In the loop-based perspective, what we really care about in a string figure is the net motions of the loops towards and through each other and such. So I have now, instead of like one near and far strings, I just am thinking about my 1 loop and my 2 loop and my 5 loop. So that means that now there's a much smaller set of moves that we can actually do, right? We can, for example, twist a loop. I can just pick this one up, give it a little half twist and put it back on my finger, and now I get this figure with this like twisted loop. Or, for example, I can move loops towards and away from me. And we'll illustrate this on the next slide. But now we've like boiled down all our motions to basically three questions that we can ask about how loops move. If I pick up a loop, is it moving towards me or away from me? Is it crossing over its neighbor or under its neighbor? And is it getting inserted through its neighbor? So what does this look like in practice? So this is the notation we use. So for example, this first picture here, that arrow pointing left says this loop is going to be moving towards us, where we are sort of at the bottom of the figure here. That underneath means it's going to be crossing under its neighbor. Or let's say if I'm looking at this like last photo on this slide, how do we read this? Well, is this loop moving towards or away from us? Well, that arrow is pointing right. This is moving away. Is it crossing over or under its neighbor? Well, it's under the 2, so it's crossing under. And now that up arrow means this is getting inserted up through its neighbor in the process. And implicitly getting put onto the next available finger.
Okay, this notation has a lot going on.
Yes.
There's like lots of layers here. Are there things people want to ask about any of the notation?
Yeah, I have a question. So there's 3 images on this screen.
Yeah.
Are these 3, do they have anything to do with each other?
These are like 3, I guess, illustrative things.
I mean, this is not like one move in 3 pictures. These are just 3 different examples of moves.
Correct.
Yeah. So the notation below is showing you what the picture is illustrating. So here,
Right.
our 2 loop is colored green, and it's saying, okay, take the 2 loop towards you, so that the green loop passes over the red loop.
Got it. Take the 2 loop towards you, so it's passing over. Okay, I see. So the pictures we're looking at are the result of doing the move from the identity. Is that right?
Correct.
Or from the starting point?
Yeah.
We should totally add that
Yes.
to our slides. Okay.
Yeah.
1 second. Even your speakers are taking notes.
Yeah.
Am I good to go?
Yeah.
Okay. So this is
I
cool.
have a
So each
question
of
as
these
well.
photos illustrates one of 8 potential ways that we can move loops sort of through and past each other.
have a
What you
question.
might notice here is that here we've used 3 distinct loops, right? Whereas in a string figure, in the end, it's all just 1 loop that's sort of been divided up between the figures, right? As opposed to 3 distinct loops. So what does this look like in practice on an actual string figure? Uh-oh. Yes. So on this string figure, we can now see that we're doing what in this case is now just twist moves on these 3 loops in the figure, treating them as if they were distinct. So at this point, we have 3 different ways to notate this, right? We can do Rivers and Haddon, which is just describing in plain English what to do, right? It says twist all the loops 1 full turn away from you. And so you end up with something like that. Storer, in the meantime, would be talking about, okay, twist your 5 loop 2 times. And in our loop braid notation, which is the last one that we introduced, now we're just saying, look, take the loop that's like first from the top and twist it, and now take the loop that's second from the top and twist it, and now take the 3rd loop from the top and twist it, regardless of where those loops actually occur on the figures. That's one further layer of abstraction we can do. And so that's cool. Now we have this very sort of abstract, even more mathy feeling notation. But just a note of caution. Because
Go
yes,
ahead.
So I think we have some questions.
Perfect.
great.
Yeah.
We can't see the chat, so we'll pull the chat
Oh,
up.
I was only raising my hand to point to Karen because she had a question and sorry, go ahead. I mean, I have a question myself too, but I'll let Karen go first.
No, go.
Right.
Well,
I just had a quick.
Yeah, go ahead.
I just had a quick question from the last one, from the last slide, and that is this. Let's take the leftmost one. I understand you start with 3 loops that are separate, and then you take 2 and you pull it over 1. It seems to me that that would be the same as taking 1 and putting it under 2. Is that a distinction, or is that not a distinction?
Yeah.
Or will you get to that?
So this is going to be a neat thing. Yeah. So like 2 over towards is the same as 1 under away.
Away.
So our notation is going to have kind of like redundancies, or we're going to have relations in the group structure that we're about to build. So the two elements that we're talking about are equal in the loop braid group. They're just written down in different notation. Does that answer the question?
Ahead. Yep. Go ahead, Ted.
Yeah, and related to this, I mean, again, my mind is going more towards the algebraic structure you're encoding. I mean, one, what I had in mind was questions of commutativity of these moves. In other words, when this notation seems to imply that you could write it either way. You're writing 2 things here, but are they necessarily always order independent, or is there is there something to worry about there?
So phenomenal question. We will be, so you're basically about like 5 slides ahead of us.
Okay.
But yes, we will absolutely be discussing commutativity and relations here. Okay, cool. So yeah, so we have this lovely notation. We suspect that it might have some group structure. So now, okay, let's go and start writing some relations for this. But just a note of caution that you do have to be mindful of the fact that, yes, in the end, we are doing this as a figure on our hands. These loops are not disconnected from each other. So for example, one thing that you might notice if you start playing around with opening A is this little relation here. So this is using Eric's notation from String Figures as Mathematics. So it looks like slightly different, but the idea is the same. So this says, take our 1 loop, move it away from us, and down through our 2 loop, and back onto the thumbs. Cool. And I'm going to do that on my other side. And whoa, what do I get? I get opening A with the thumbs twisted. That's cool. So have we discovered a new relation for this group structure? Well, we will, show you this in more detail later, but it turns out that this isn't actually anything that's fundamental to like the motions of loops. This is something that is produced just by the structure of opening A. So that to say that we might need like a little bit more of a framework here than just what works on opening A.
Just a bit of historical context here. So Eric has an undergrad and a master's in math, and then went and did his PhD in anthropology, and has been doing this kind of math anthropology stuff with string figures for a while. And he stumbled onto this relation. So it's true that passing the first loop through the second and putting it back onto your thumbs produces a twist. And I guess, oh gosh, 2 years ago now, I was on sabbatical, and he said, "Hey Parker, is this true? Like, is there a framework for proving this?" So Eric came to me and asked, what is the structure of loop manipulations? What is the underlying mathematics there? And at that time we had the Storer calculus. We didn't have loop braid notation. So it was something that we goofed around with for a sabbatical, and we found ourselves in the land of algebraic topology. So anyway, sorry to steal your thunder. I just wanted to say that there's a relationship here among Eric and I, and we know where this question came from.
So, okay, do we have ways of like building relations that are actually a little bit more rigorous that we can actually check will hold true for like all sorts of starting configurations? That's sort of the fundamental question here. We're asking what relations always hold among loop manipulations. So this is where group theory comes in. I'm going to go out on a limb and assume that this audience is already familiar with what a group is. Yeah.
If you're not, please speak up now. We have tons of time for questions. If you've never heard of groups before, please let us know.
I never heard of groups before.
Perfect. Today is the day that you learn a new thing. That's great.
Great.
Cool.
Okay. So on the screen, you see this very sort of formal definition of a group. And we can certainly go into that, but for now, the most important thing is a group is a collection of mathematical objects with certain nice properties that we can leverage. And specifically, a lot of what groups are of taking these like elements of the group, which are its sort of basic building blocks, the little chunks of the group, and building those up to make more elements in sort of these structured ways. So in the case of groups can look a lot of different ways, right? These can look like rotations of a shape, which you can combine, or these can look like, for example, a braid, where you can combine various ways that you can interleave strands. And in our case, in string figures, it turns out that these little chunks that make up our group are okay.
Wait.
I'll let the actual mathematician talk about this.
No. So like we now have the heuristic of it,
Yep.
right? It's things that we can multiply together, but the multiplication has to have certain properties. So there has to be, inside your group, there has to be an operation of doing nothing. You have to be able to take your cube and just leave it. That's called your identity element. There also has to be a notion of undoing things. So you should be able to apply an operation and be able to undo that operation. And the product has to be associative. You should be able to re-bracket things as you like. So the definition that I've written on the slide is like, I think van der Waerden, very formulaic, but in the early days, people didn't even define it. They'd just be like, oh, the collection of symmetries of something. Collection of symmetries is the right way to think of a group. Any place where you can do an operation and undo it will be a group, essentially. Did that
Parker?
clarify?
Parker,
Yes.
I think Ted also has a question.
Yeah, Ted.
Yeah, hi. I just wanted to clarify. I mean, I raised my hand so I wouldn't, jump in. Otherwise, at an opportune time. But I wanted to clarify again for those who are not that familiar with the idea of what you're trying to do, because you kind of mentioned it in passing just a few minutes ago, I guess Ness did, which is that in talking about that particular discovery of Eric's and sort of saying yes, but it's not, we figured out it's not exactly what we were looking for, or at least some implication of that, which points to the fact that when we think of groups, we're thinking not of the objects that are being manipulated, but of the manipulations themselves as being objects. So it's a process of abstraction that is central to mathematics. And, I want to elevate that as something that we actually talk about, where essentially your whole talk is an exemplar of that, of where we have a concrete thing that we're manipulating, namely the string figures. But what we're interested in are the properties like identities and so on of the operations we do on the strings. So we imagine this abstract space where the operations are the things themselves, and we're talking about them, illustrating them by doing them. And so, for example, I think what Ness was talking about earlier was the fact that that maybe that property, I mean, I'm imagining this, I don't know, I'm conjecturing, maybe you guys will clarify it later, but that property that Eric had discovered was a property of that particular starting string and not a property of the transformation in general that could be applied to any starting configuration.
Yeah, yes.
Yeah.
Yeah, one of the things that was neat about this collaboration with Eric was it just took us months and months and months to figure out the right question. Like, okay, do we want to study the context in which these are the relationships that matter, or do we want to study the context in which relationships always hold, or like even just thinking, oh wait, we're looking for a group structure. It took us a long time of many meetings. Another bit about that research was we were also trying to explain this stuff to a computer. So we were coding this in Julia, and computers are very picky about what questions they want answered and what questions they want asked, and having to program this was part of the motivation. That's a whole other talk.
Actually, interestingly, just with that, because it links with other talks we've been having recently in Relatorium, when you're trying, as is very natural these days, for mathematicians to try to tell computers what we're doing so we can interact with them. Computers expect something very precise to be said. Okay, this is the goal that we have. Tell me a goal and I'll do it. Whereas that's not how we do math. We entertain multiple goals, and we're not sure, as you're saying, you guys didn't set out to find the group structure. You realized that was a thing to find along the way. So that's a kind of an obstacle as we're trying to involve more AI mathematicians in our work. But yeah, thank you.
Onwards and upwards.
Onwards and upwards. Yeah. So one interesting thing about groups is, for those who haven't seen much of groups, is that they have these things called generators. So these like sort of very fundamental operations from which we can build all our other operations. So in the loop group, which is what we're calling or loop braid group, which is what we're calling the string figures, what are our fundamental operations? Well, you've already seen some of them in the notation that we introduced earlier, and now we just get to formalize them a little bit, right? We can say that, for a string figure with like n number of loops, because we're certainly not limited to 3, we can like for each of those, for each loop, we can twist it, or we can move it over its next door neighbor, which is like the loop away from it, or we can sort of just cross it without going through, or we can actually insert it into its neighbor. So twist, cross, and pass are what we're calling these. And we've you can see these diagrams a little bit more abstractly. And what this means, oh yeah, and so how does this actually show up on a string figure? Well, in a string figure, as we perform these manipulations, in the middle we get this sort of central tangle. At the edges we just get where our fingers are holding the string, and then in between those two, we have sort of this braid region forming as we pass loops around and through each other. And so that's very cool, because we already have this field of mathematics that is dedicated to examining the relations of braids, the braid group, right? Which in this case deals with just saying like, okay, look, we have so many strings. What are all the ways that we can cross them in combination with each other? And what's great about that is that we already have some braid relations defined for us. We have these, for example, this idea that we'll later call like twist commutivity, right? If two strands are interacting somehow and crossing past each other, and then like later on the figure, two other strands are crossing each other, you can see that those two interactions don't affect each other. You can perform those operations in either order and it'll all work out to the same braid in the end for our definition of sameness.
Yeah. So just about the diagram on the slide, there's this orange diagram and red diagram, and this is showing that you can take the orange crossing and move it over top of the red crossing. Those two crossings are happening kind of in independent places. So the braid, the 4-strand braid on the left is equal to the 4-strand braid on the right, and you can just imagine moving. So that's twist commutativity. What's the braid relation?
Yeah, so the braid relation is a lot of symbols that I'm not going to read out loud, but what this looks like intuitively on our figure here. So if we look at this red, green, blue figure, if you look at the sort of red-blue cross, you can see that we can sort of slide that past the green string on our diagram without really affecting what the green string's doing, right? We can just like kind of take that crossing and pull it down, and that's kind of the same braid in the end. Intuitively is what the braid relation says. Do you want to say? Okay, great.
Yeah, the braid group's great. Comes up in algebraic topology all the time.
Yes.
Super duper like group that launched 1,000 papers kind of thing.
Yes. So that's really cool. Because now what that lets us do is we can go back and say, look, all these relations that we've found, are those actually like real in some sense? Are these actually relations of the braid group or the loop braid group in our case? And we can go and we can say, no, actually, if we go ahead and we use our braid visualization tools for this, we can see that these are not, in fact, the same move. These two sets of moves do not generate the same braid. So, you know, the one on our right is literally just, you know, twisting the one loop twice. And then the one on the left here, you can see that if you try to sort of straighten out this braid, if you look at that green string on the top, that's just gonna like straighten out fully. That's fine. But if you look at the green string on the bottom, and you look at how that interacts with the red string on the bottom, you can see that if you pull those two apart, they're going to sort of get caught on each other, right? The red string is sort of wound around the green string in a way that means that they can't separate. And of course, you know, there's of course like a mathematical language to describe why these aren't in fact the same braid. You can see there are some moves that just don't cancel. Their inverses don't ever end up being next to each other. But using this technology, we can say, look, now we can say with confidence that whatever relation we've discovered about opening A isn't something universal to this collection of objects that we're trying to examine.
Things people.
Oh yes.
Things people want to ask there? Things people are curious about?
Hello, this is Matt Insall in Rolla, Missouri. I got to meet Nessa last week. I really enjoyed learning what she's working on there. I had a couple of comments, not exactly questions, but it might lead to questions. So the first one is that I came in late, and one of the first things I heard from you is you mentioned the diffusion theory, and I wanted to mention that that you can connect to a study of that I have a book about that I didn't write. I didn't write it. I found it, and I found it very interesting, and I'd like to point out, you might find it interesting as well. It's called the diffusion of innovation, and it's really closely related to the ideas you're talking about there. And examples that they give in there is whenever nurses went to South America and talked to people in villages about how they should boil water before they drink it, they faced all kinds of obstacles culturally, and whenever when they did this, they don't talk about the mathematics. That's the thing. You could contribute, and I would love to participate in that if you want to. Anyway, the diffusion has obstacles, and the obstacles can be represented, of course, by friction and network and things like that. Anyway, I wanted to move on. The next thing is as you were mentioning multiple strings, and Nessa mentioned that last time, but this didn't hit me till this time while she was talking about that, and you were talking about
Matt.
Matt. Yes.
I'm sorry. I'm the moderator. Could I, unless Parker and Ness, you want him to continue, could I ask you to hold this until the end so they can get through the slides until the end? And then is that okay? I apologize if that sounds rude, but I think they've just got a few more slides, and then we can. I'll go exactly back to you.
Yeah,
okay. Thank you.
We've built in a lot of time for questions. So when we rehearsed this, the talk was like, I don't know, 40 minutes or something.
Like
so thank you, and we'll have time for the questions at the end for sure.
Yeah.
So onwards, upwards.
Yeah. So the cool thing about these braid relations is that they can let us say what's not a relation. But the other thing that they can do is they can say what is a relation, right? If we translate our string figure into the language of loop braids, suddenly that means that we can look at this and we can draw conclusions about what other string figure algorithms this might be equivalent to. What other series of moves might produce the same figure in the end. So that's very cool. That's a very powerful tool. But one problem that we actually ran into during our research is how do we actually verify that these work, right? Because like this whole time I've been trying to show you Eric's relation, and I've got my string all tangled up. And I've had to sort of like awkwardly sort of ooch my thumb around, and you can't really see what I'm doing. And it's not great if you've only been working with string figures for a while. So one thing we thought was like, it sure would be handy to have an extra free hand when we're working on these string figures so we can actually carry out these loop-based manipulations, because they're a whole lot harder than string-based manipulations, right? So this is where tacking comes in, which is something that we sort of happened upon when we were doing this research a few months ago, where the idea is that instead of one person making a string figure, now we have two. Yeah. So we'll show you how that looks in practice, but basically Parker, who is sitting on my left, is going to be the left hand of this figure. I'm going to be the right hand. And now we can go ahead and perform our loop manipulations with our free hands. So
just one sec. So we're not going to teach you this figure. This is Kura again from our introduction, but we took the English prose description of this and turned it into this loop manipulation notation. And it's hard to do it. To do this as one person, to do the loop manipulation is actually quite tricky. So let's do it as two.
Yeah. So the convention is that we start from opening A, right? And now we can just go ahead and follow these instructions here. So the first one says we are going to take the 3 loop and twist it towards ourselves twice. Another useful thing for tacking is that you can do one person moving at a time. All right, and now we're going to take our 1 loop and move it, over and away from us and onto the next neighbor. Great. Let's move it a little closer. Okay, and now we can take the 2 loop and move it under its neighbor. A little note here. Notice that, if we want to move this 2 loop, where's it going to go, right? Because we need it to move under this loop, its adjacent loop, the 3 loop, but we don't really have a place for it. This is actually sort of a trade-off that comes with the abstraction of describing loops without reference to what fingers they're on. It means that sometimes you have to do this little loop-based shuffle to get the actual loop braids to work out. So before we do that, we're just going to shuffle this 3 loop onto our ring finger, and then we can do the rest of the figure as normal. So now we can take this 2 loop, move it away from ourselves under its neighbor. The astute among you might notice that this is always the same loop that's moving, which is cool. Now we can take this 3 loop and move it over and towards us. Finally, we can take our 2 loop and move it towards us down through its neighbor. Right? And then the last thing, which isn't written in this notation, but is sort of implicit, is that we're going to drop the 2 loops. And if we've done this correctly, that's a Cora. Woo!
Yeah.
Yeah. So now we've actually verified that the loop relation produces Cora, which is awesome. And so the last step, which is very important, is to take your free hand and give your partner a high five. Cool. Cool, cool, cool. All right. So what does this loop-based perspective give us on string figures? Well, now we can actually look at these commutativity relations that we've been talking about earlier, right? We can, for example, talk about the commutativity of twists. And in fact, if we just stare hard at this enough, like just getting some intuition, if you look at these 2 twist moves on the top left, you can sort of imagine just like grabbing them and dragging them along the figure and down through like past the rest of the interactions here. And what that gives you is you can just imagine the rest of the figure shifting to the left is this, right? We've just moved that twist move all along to the end of its path. And in fact, we can, we can define this formally, and more on that later. But like another way to verify this twist commutativity is let's do Cora again, except a revised version of the algorithm where we save those twists for last. So back up here. All right, so we're going to take our 1 loop, move it over its neighbor. I'm going to do that little loop shuffle up just to make space. We can take our 2 loop, move it under its neighbor and away from us. 3. We can take that 3 loop and move it over its neighbor and towards us. 2 loop, move it over its neighbor and towards us and inserting through in the process. Great, and now we can do that long-awaited twist move on the 3 here. Towards, yes. 1 and 2. And now, moment of truth. Does the relation hold? Do these moves commute? Well, release. And there's Cora! Woo!
Yay.
Yay! So what is this saying formally? Well, it's basically, actually, I'm not going to read that out formally. But what this is saying is that, yeah, if we have like some cross move happening and then a twist move, though that twist and that cross commutes. Though notice that and though notice that here, like you do have to be careful because like the names of the loops are defined in relation to each other. So this n loop here becomes the n-1th loop here. And the very cool thing is that turns out we are not the first people to happen upon this idea of loop braid groups. These are actually well studied in the literature, and we have sort of these like 30 odd loop braid relations. And cool. Now we've basically unlocked this new like analytical tool. So we can stop thinking about string figures quite as much as just like these interesting games to play and say, look, these actually have this underlying structure.
Cool. Yeah. All right. So thank you for coming and playing with us today. Questions, comments, ideas. Yeah, we'd love to chat more about any part of it.
Matt, maybe we could, well, first of all, thank you so much. I think that was fantastic. Thank you. That was great. Excellent. I will need to practice a little bit more, I think, though. Matt, maybe we can start with you.
Thank you, Karen. I was in the middle of typing another question that came to me while they were talking about that. So the earlier thing I was bringing up was that it seems to me that one way to think of what you're doing is recreational mathematics, and another way is, of course, pure mathematics, because it's the great braid group, which is, I guess, fundamentally usually considered part of pure mathematics, although it's got applications. But I think that you may find that you can develop these algorithms for, since you're doing this for an arbitrary number of fingers on each hand, you can probably sell this to the textile industry. Because after you've made the string figure, when there should be some way of tying it off and pulling a knot, and you get a different kind of knot for each of the different figures that can be, if it's studied carefully in the textile industry, this can make very interesting patterns that will be of use to them in the adapting creative designs to fabrics and things like that, and sell them to drapery companies and things like that.
Nice. So just a comment in response to the textile thing. So this work with Ness grew out of a reading project I did with another student, Samira Goder. So in the fall of last year, I worked with Samira, and we worked on this textile tradition called loop braiding. So when you braid 3 strands, you're usually thinking of holding the individual strands and kind of moving them. But this gets unwieldy with 10, 15, 30 strands. You just don't have so many hands. So there's a style of actual braiding practiced by real people in the real world called loop manipulation braiding, where you're using whole loops. And I could come back and tell you about that. That'd be a great seminar talk, a relatorium talk. So yeah, there are definitely textile things here. And one of the nice things about this research is that it simultaneously formalizes string figures and this existent tradition of European loop braiding, which we didn't touch today.
So unless somebody else has a question, I have another comment that I wrote in the chat that's related to this. While I was writing it, the reason it came to me is that you were doing this with 2 people with 1 hand each, except that you had an extra hand. I saw that Nessa was reaching over and moving things with her hand. How do you envision this being done if each of the agents, and I think of machines when I think of of this, because otherwise I guess you could think of 2 one-handed people, one with a left hand and one with a right hand, versus both of them being left-handed. How do you envision modifying your description of how things go so that it adapts effectively and efficiently to that scenario that might be of use in various industrial applications, or also in just the recreation for 2 people doing loop figures, where they restrict their use of the loose hand?
Okay, so I think the question is, like, how do you do this without the extra hands? Is that essentially it?
Yes.
So the extra hands thing, this is like I guess a pedagogical innovation.
Yeah.
Like we're doing tacking as a pedagogy tool to demonstrate how to do these. So the talk we're giving now is a rehearsal for the talk we'll give at Bridges, where we'll be teaching people and we'll be walking around saying, okay, can I help you with that? So this is a teaching tool. One can, with much practice, do these loop manipulations solo with your 2 hands. You don't need the extra pair of hands to do this, but it's not suitable for beginners. It takes some practice.
Yeah.
Right. So that means that it has to go into your notation as a communication tool between the 2 people. Yeah, that's what I was headed for. Yeah.
Totally. Are there other comments, questions, improvements, advice?
So I remember playing one of the ones I used to play with string when I was little. Big surprise that I knit now. And I remember the the idea is that you take your fingers and you pull like this, right? And you're able to manipulate the loops in the way that you're saying by going in and out with your fingers, yes?
Mhm.
Yeah.
So I have to think though that there are some twisting, for example, is a little bit more difficult, but there must be some that are easier to do just by yourself by manipulating your fingers, and some that are more difficult, or I'm going to say almost impossible.
Yeah, so one thing that we didn't really dwell on is like what do string figures look like outside of these loop braid manipulations, right? Like, you know, the majority, like the vast majority of string figures are just designed for one player. So you know, absolutely there are some string figure moves that are you know, easier to carry out than others, right? Like, you know, you could like straightforwardly fetch a string, but you know, twisting always just runs the risk of dropping the loop like I just did now. Or you know, you have these like string pickups that are like fairly challenging, like where you have to like duck through a loop and pull, if I'm making Cora here. And so
I
sorry,
guess
what was your...
I guess my question is, some of those manipulations you can, with some dexterity, kind of do.
Yeah.
My question is, are there some that you can't actually do, that you will need a third hand, or like Matt was mentioning, a machine will have a little bit harder time?
Yeah, so I think to summarize what Ness was saying, like most of these manipulations are not done at the loop level. Most of them are done individually, and it requires a great deal of dexterity. So like there's a skill gradient here. So like in other work, Ness and I were working on a particular figure called Chief of Two Trees, and that's a whole other story. And she's just more dexterous than I am. Like there's a particular pickup that I just can't do because it requires like my thumbs reach into the middle of the figure and pick up this one random string. So the loop braid notation and the loop perspective is sort of an algorithmization of a particular aspect of string figures, but most string figures are done string by string, finger by finger, and there's a broad spectrum of how hard they are for individual people to do.
Yeah.
Like, yeah, it's fascinating. It's like an endless hobby. You can just go forever.
Yeah.
Are you gonna do two cheese and just show off?
Yes, I'm gonna show off. Yeah, so this is another project that, yeah, could be a presentation all on its own.
And that involves, in the middle of what you just did there, there's something that requires, I don't know, 50 hours of practice or some insane number.
Yeah, yeah.
So
as for the question as to like whether there are moves that are simply not doable, so in the like loop-based perspective, I would tentatively say, and like it depends on your definition of doable, but you know, because there's such a limited set of moves, right? Like twist a loop, move a loop through another loop. I'd say for sufficient dexterity, probably not. Now, are there like string figure moves that are basically not humanly possible to carry out? Well, kind of no, because string figures are this like inherently human activity. Right? You know, these are designed to be made for human construction. In fact, there's this interesting little niche of string figure research, which is like, can we take this figure and like remake an equivalent figure where the moves are just like a little bit nicer to carry out? But yeah.
It's a rabbit hole. It's a deep rabbit hole. Are there other things people wanted to ask?
I think Ted, maybe you have some.
Yeah, I mean, yes, thank you, Karen. I mean, I in fact, I had started thinking of a different question, but then your question kind of maybe changed it a little bit in my mind. But I see now, I think with what Nessa just said, I understand your perspective better. But I wanted to abstract it. Maybe this is where my intuition matches a little bit what Matt had in mind. What if we had, it seems as though what this research so far is based on is the algorithm itself. In other words, you're already starting with something that's constructible, and you're looking for ways to represent that construction and maybe show equivalence classes of constructions that lead to the same figure. As opposed to starting with the figure itself, like, for example, considering this configuration of, loops in space, in three-dimensional space, and or some configuration of loops in three-dimensional space, and try to answer the decision question of whether it's constructible with two hands or with what's the minimum number of loops you have to start with to manipulate. Or do you see what I'm saying? Where it might be that there's some figures that are only constructible with three hands. You can't do it with two hands. So you have to be some sort of alien that has three hands to do that. Of course, that wouldn't be interesting to any human if they were starting from an algorithmic construction, right? But to a mathematician, it might be interesting as you're trying to find equivalence classes of like string diagrams, So I wonder if you're aware of any research that starts from the figures and looks back at whether an algorithm exists to construct them or not, or what's the minimum instantiation.
So this is enormously complicated. So we're skirting around so you're talking about decision problems and recognition problems, and these are just hard. So recognizing it, so someone hands you a diagram, an alien, a string figurist, Ness, hands you a diagram, actually determining if that is a knot or an unknot algorithmically was very hard. So this was a problem from, 1880 to 2017 is the unknot recognition problem, which was famously resolved by Mark Lackenby. And I remember being a grad student, that being a ton of news, oh my God, there's a polynomial time algorithm to recognize unknots. People got excited about that. So just recognizing is something an unknot is hard. It turns out there is a polynomial algorithm for it, so we're fortunate. It's not impossibly hard, but it's a hard problem. But there's interesting stuff. So the braid group is really nice. It has a recognizable word problem, so you can solve the word problem algorithmically in the braid group. But there's difficulty. So anything that you ask about braids has a flip side about knots. Every knot can be turned into a braid in a known way. So it turns out the braid group has a solvable word problem, and that's nice. But it turns out the conjugation problem is this braid conjugate to another braid is enormously difficult. That's still open. We have no idea. So questions of can a particular string figure be constructed? They're much, much harder when someone's just handing you an arbitrary diagram. They're enormously algorithmically difficult. And I don't know, it's kind of silly that right beside this children's game is open problems and knot theory. I love that.
Now that I have a comment or question related to that. So now that you've got the groups in mind that you have that are of interest, that is the ones that correspond to string figures and the manipulations of string figures. Isn't Ted's question really equivalent to, first we think of, if you show someone the string figure, that string figure sort of represents a sequence of operations, but is it in that group? So if it's not in that group, then presumably a human can't do it. So it's a question of, is it in the group or is it not? Unless you have not captured all the generators that a human can perform. And that's basically where I was headed. That's basically what I think. And I wrote the word in the chat that I didn't send it yet. I thought I did. Ted : factorizations ? So you start with the final result of operations, or you think it is, and then you try to factor it. In linear algebra, we have this procedure, the Gauss-Jordan elimination, which you can use to factor a matrix, if you do it carefully enough, into specified kinds of factors. For example, there's a limited collection of those operations for the people who are not familiar with linear algebra is guaranteed to give you a factorization of a matrix into a product of elementary matrices. And those are the elementary steps that you're allowed to do. And but you have to be very careful how you attempt to find that factorization. And then there are other factorizations that are done in similar ways and others that are done in other ways. The singular value decomposition is a factorization and things like that. But here we're talking about a group element in the permutation group of some set. Is it in your group? And that question, what's a procedure to decide whether it's in that group or not? And I think that's perhaps doable by similar kind of things that I'm talking about. You basically start with it and try to use your generators to unknot it. It's not really unknotting because it might not be a knot, right? So it's a loop, right? So it's perhaps not really a knot. It's like a braid. Unbraid it. Yeah, that's where it was headed. Yeah.
Yeah. So okay. So there's two directions of this. So there's a kind of like arts and crafts, human element, the kind of anthropological thing, and yeah, taking one of these string figures and then like figuring out a loop manipulation sequence is fun. I don't know. I get up at like 6 in the morning and do that. It's actually just fun. So oftentimes, given a string figure, you can just work backwards until you get to opening A, and then you're like, oh, now I have a construction. And then there's the mathematical question of like, given a braid, is it in this loop group? And that's a decidable problem. And the decision algorithm, which I think was first published by Joan Berman. I'm not sure exactly who published, but anyway, you can decide if it's in the loop braid group, and if it is, you'll get a product representation of it. So in the arts and crafts way, yes, this is a fun pastime. And then mathematically, yes, there's a factorization algorithm in the sense that you're thinking of, Ted. Oh, just one thing that you said in your comment was like, are there things that definitely aren't in here, aren't in the loop braid group? This is a very simple figure that is not in our loop braid group, because the strings are just, this looks a lot like opening A. It's opening A with the, oops, I've lost my camera. I've lost everything. Oop. Okay, we're back. So this is opening A. And then we exchange these two loops. We exchange the index loops. And now we have strings that aren't monotonic running from side to side. So the braid region here it turns out isn't an element of the classical braid group. So there's definitely aspects of the human practice that we're not capturing here, and we're sort of skillfully avoiding by defining the problem the way we want to.
And picking nice string figures that are very braid-like.
Yes. Yeah, totally. Cool. So that takes us to 12:45. Irfan, do we usually wrap up around this time?
Well, we can, but we can also keep going on depending on if you have time and if people have questions.
Are there any more burning questions? I'm only booked at 1, so. Oh, someone is coming in right now.
Yeah, I don't know this. Anyway.
I mean, what you just mentioned, Parker, made me think that the non-monotonicity of the one that isn't representable in this group, made me think of, invariance, monotonic invariance or whatever, that one could you know, like that one could conjecture could be easy decision tools, like counting over loops, you know, polynomials or whatever, like we do with knots. Is so it, you know, in your case with things that you know, deciding the one that you showed us was not representable in the group was kind of an easy thing. So you know something that we don't know. This seems like the beginning of another talk, but but is it a talk that starts this way, or is it a talk that starts somewhere else and you recognize that the two actually are related? Do you see what I'm saying? Is that starting somewhere else, that story?
Yeah, there's a kind of course that I want to give called Unknot Theory. Classically, we offer knot theory courses. I think Lisa offered this course. There's also a course that I want to give, Unknot Theory, because the unknot is fascinating. All these, like, they're hard things about just recognizing unknots. And I think that the question about invariance and like polynomial invariance of string figures and this kind of thing, like polynomial invariance of braided string figures, that would fit into unknot theory, the course, but that's a different talk than what we're doing today. Yeah, it is.
Now, so I have a related question to the one that you showed that is not part of your loop group. Is there a manipulation that you can add to your generator list so that when you generate the larger group from your new generator list, you get that one? Do you know that one off the top of your head?
Yeah. So okay. So going back here, we defined the braid region, and then we talked about this thing called the central tangle, which is this central strip. We have not talked very much about the central tangle in this talk. In our formalism, that unallowed move gets sucked into the central tangle, and then we sort of don't worry about it. So Berman, Joan Berman, is the person who did a lot of the sort of math side of this, and she has a great paper, stabilizations of the unknot. I'll send the talk to I'll send the thing to the organizers, but she gives exactly 2 operations that generate every possible unknot. One of them is applying a single twist, and then another one is flipping across what's called the pole axis. So if you are allowed a single twist, and this thing that's like exchanging the 2 loops that I just did, then you actually get everything. Yeah, so that's, sorry, I think it's Markov's theorem without stabilizations by Berman. I will send it to Irfan, but that's like that's deep into the math side of the picture.
Yeah, but the one you showed, is that if you add that one as a generator, do you get the twist and the reflection? That's so the question becomes, okay, so do you get everything by adding that one figure that you talked about, or do you not? I presume not. I presume
right,
that you miss the twist or you miss the reflection or both.
Yeah, so I think Berman's thing is that actually if you have this exchange, this loop exchange and twist, you get everything, but that starts to kind of diverge from the arts and crafts practice. Like there you're like really asking a very mathy question.
It's a mathy question.
What's the minimal set of operations that I can do? And that's answered and in the literature, but that's sort of deeper into the math.
Okay.
Cool. Well, thank you very much, friends. It has been an absolute pleasure. You guys are a great audience. You ask great questions.
Thank you.
Thank you very, very much, Parker. And Ness, that's fantastic. I see there's some virtual clapping going on. That's wonderful. Are there any other questions? Any other comments? I thought this is fantastic, and I've been playing with my string now. And what I've been trying to do is figure out the only string one that I know, or the only game one that I know, is this one, the teacup. And I'm trying to figure out, with the 3 moves that you mentioned, how to make the teacup. So when I figure it out, I'll let you know.
All right, all right.
So
I
far I haven't made it.
I just have one comment I want to make. I was so captivated by the complexity, the sense of your string creations, and I couldn't escape comparing the complexity and the fun of what you were doing, and trying to make some metaphorical connections with the knotty social problems we're facing right now. And I would say that the ideologies that are driving the polarization at this current moment might be analogous to the syntax logically that guides the construction of the string diagrams, and that might point to the embeddedness of ideological beliefs and how they make solving social problems so difficult. And if you keep doing what you're doing and make it look like as much fun, perhaps some of your energy and spirit and vision can translate to some of our policymakers and politicians. Maybe there's some insight that you might give them to untangling our knots.
Yeah. Spoken like a true Quaker. It's good to see. Yes. Yeah, there's, one of the things that when I think about these string figures, they're in everyone's hands. Everyone has a piece of string somewhere at home. And we spend so much time living our lives like this now.
Yep.
And if we step back from the social media discourse, the Twitter discourse, all that kind of stuff. Oh, I've lost the picture. And went back to these simple things that are accessible to everyone, and we find that life is much simpler. Life unknots itself in a way you wouldn't expect. Yeah. These are, there's something here about society, finding a good language, rejoicing in the beautiful simplicity of life.
Briefly, I wanted to say that I really like Grady's comment, because in a lot of ways, it's like what he often does. It's a kind of application of abstraction. That is, it abstracts or he applies the notion of abstraction. It's more than just the abstraction. That is, you've applied abstraction to this human activity, and he sees another human activity and sees the analogy between them. And in a lot of mathematics, that's called an isomorphism or syntactic transform or a natural transformation or a faithful functor or a faithful representation and so forth.
Thank you.
Thank you. And thank you, Parker and Nessa. Very, very nice talk.
Yes, it was wonderful. Fantastic. Okay, does anybody have any other comments or questions? Once again, thank you so much to Parker and Ness. That was really, really great. I hope you read the comments here about how many people very much enjoyed your talk.
Thank you.
Okay.
Good to see you again. Be well.
And just as a reminder, it will be on the Relatorium YouTube channel if you want to re-watch it